Welcome back to ECE 320A. We're in Unit 11. I may have misspoken last time. We were on video 2 in Unit 11, and I may have said Unit 2, but I think you know what I was meaning. This is now video 3 in Unit 11. You have a homework assignment. Reading material is Chapter 15. That's on active filters, and we have a final exam coming up at the end of Unit 12. In this video, what we want to talk about is how do we modify our circuit parameters, our R's, L's, and C's, if we want to change either the magnitude of those parameters or of the circuit, or we want to change the frequency. We're not always going to be working with frequencies or poles at -1 or zeros at -1. So how do we change those to provide the frequencies that we want for our bandwidth and maybe a parameter that we want? Maybe we now need to go to the stockroom, and the stockroom has this surplus of 1 microfarad capacitors. Oh, it'd be nice if we could incorporate those into our circuit. So now with the magnitude scaling and the frequency scaling of circuit parameters, we will actually be able to make that happen. We'll be able to achieve the frequency response that we want, even though we might be forced to use a particular parameter value of, let's say, 1 microfarad for a capacitor. Now that, once we've locked in the capacitor, that now imposes particular values for the resistors and the inductors. But here we're assuming that the more challenging part would be to match the capacitors, and it will be easier for us to actually obtain these resistors and inductors that might have more unique values. So let's now look at working through this topic of scaling, and in particular magnitude scaling and frequency scaling. And it's really addressing this question: how can we obtain the passband that we want? So now here's a particular bandwidth while still using, let's say, capacitors that we have available from the stockroom. For example, maybe we want to use a 10 microfarad capacitor in our circuit. Well, that means that we probably need to perform frequency scaling and magnitude scaling to make this happen. And before we get too far into this magnitude scaling topic, let's now talk a little bit about notation. And this may be a little bit inconsistent, but hopefully I'll stick with this. I'll try to use subscript 2 to mean the initial value, or maybe I will be referring to that as the old value, and subscript 1 is the old, subscript 2 is the final value, or the new parameters value. And if we're trying to scale the magnitude, then what that means is we want the new magnitude, let's say Z sub 2, to be a scaled, or a magnitude K sub M different from Z sub 1, where here this magnitude scaling, this constant, is going to be positive. Let's say that the impedance Z sub 1 was initially 1, and we actually want Z sub 2 to be 4. Then we would pick our magnitude scaling K sub M to be equal to 4. Let's see what this looks like for particular impedances. Let's look at the resistors. What's the impedance of a resistor? As a review, Z sub R. Now we want to see this in terms of omegas, in terms of frequencies. How do we describe the impedance of a resistor? Hopefully, you're saying, wait a minute, what's he trying to do? Confuse me? The resistors are frequency independent. So the impedance of a resistor is just R. Now, The other columns, the inductors and capacitors, are a little different. What's the impedance of an inductor? Well, if you're thinking Laplace, you're saying SL. Well, now we're dealing with frequency relationships and not complex frequency. Now we want to let S equal j omega. So now the frequency relationship of an inductor is now j omega times L. Similarly, for capacitors, its impedance is 1 over SC. Well, S is now restricted to be along the imaginary axis, so now we have 1 over j omega c. So let's see how this plays out. We said that the new is equal to k sub m times the old, or z sub 2 is now k sub m times z sub 1. Let's see what this translates into relative to values of our parameters, where now we'll say r sub 1 is the old or the initial resistor value, and r sub 2 is the new or the final value. In our case, then, we're saying that r sub 2, z sub 2, is going to be k sub m r sub 1, and there is now our relationship between old and new, or initial and final, if we magnitude scale a resistor. What about the inductor? Well, now z sub 2, this is the impedance when we have the new value or the final value of the inductor. We need to use this blue formula with L sub 2. So now we have j omega L sub 2. And we want that to equal this magnitude scaled impedance z sub 1, or the old impedance. So we now have k sub m times j omega L sub 1. And now we can start canceling some of the common terms or factors on the left and right. The j's are the same on left and right, so we don't have to worry about those. The frequency is the same. And now we can see the relationship between original or initial inductor value L sub 1 and the final value L sub 2. L sub 2 now, that's all that's left on the left-hand side. We see if we magnitude scale our inductor, that will now be k sub m L sub 1, and there is our magnitude scaling. Let's do the same kind of analysis for the capacitors. Again, we're using the basic relationship of the impedance of our capacitor, 1 over j omega c, but now we need to use that for c sub 2 and c sub 1, so that z sub 2 is now 1 over j omega c sub 2, and that's equal to k sub m times z sub 1's impedance, which is 1 over j omega c sub 1. Again, we can start to cancel similar terms on the left and the right, or we could multiply both sides by j, we could multiply both sides by omega, and now we hopefully can see that if we wanted to, we could actually rewrite this right-hand side as 1 over, I'll go ahead and include the j omega, c1 over k sub m, and the j omega is gone. So that now if we compare pieces in that expression, hopefully you can see that c sub 2 is equal to c sub 1 over k sub m if we magnitude scale the capacitors. So there's the magnitude scaling piece. Let's now talk about frequency scaling. With frequency scaling, we want the impedance at the final frequency to equal the impedance at the initial frequency. So here you might think of, oh, if I had a low-pass filter with a bandwidth of 1, I don't want a bandwidth of 1. Maybe I need a bandwidth of 10. Oh, how do I now perform or find the right parameters in my circuit to move from a bandwidth of 1 to a bandwidth of 10? Here we're going to say, oh, we're scaling frequencies, which means the final frequency, omega sub 2, is a scaled version of the initial frequency. And we want the impedances to be the same. We're worrying about magnitude scaling earlier. Now we just want to worry about frequency scaling in this particular segment. So that now we're just changing the frequency, and we want the impedances to be the same. So let's look at the resistors. What's the impedance expression for a resistor? And that you should be very comfortable with. The impedance of a resistor is just the resistor. And now we want Z sub 2 to equal Z sub 1. Well, if the Z's are just R, we can see that R sub 2, in fact, is equal to R sub 1 when we frequency scale. The resistors are not a function of frequency, so they don't change if we're doing some kind of frequency scaling. In our circuit, we would just leave those resistors alone, unless we did a magnitude scaling. What about our inductor? Our inductors now, the final inductor, Z sub 2, has an impedance at the final frequency of J omega sub 2 L sub 2. And that, though, remember how we've related omega sub 2 with omega sub 1. Omega sub 2 is actually this K sub F omega 1, and that's now scaling L sub 2. But in this frequency scaling, we want Z sub 2 to equal Z sub 1, and Z sub 1, that's now the impedance of the initial inductor at the initial frequency, so that's now J omega 1 L1. Now let's examine what happens when we connect those two or compare those two expressions. The J's we can cancel. The L1 and L2 we are different, so we have to keep those, but the omega 1s are the same, so we can get rid of those. And I hope that you can then see that from that highlighted expression, we have K sub F L sub 2 is equal to L1 when we frequency scale inductors. Or if we wanted the final inductor value in terms of the initial, then if we know what our frequency scaling factor K sub F is, we simply divide the initial inductor value by K sub F to find the final value of our inductor, L sub 2. So L sub 2 is L1 over K sub F when we frequency scale. What about capacitors? Let's do the same analysis. Z sub 2 is the impedance at frequency 2 with the final capacitor C sub 2. So this is 1 over J omega sub 2 C sub 2. But again, omega sub 2 is connected to omega sub 1 by this frequency scaling factor K sub F. So we now have J K sub F omega 1 C sub 2. But we want that to be the same impedance as Z sub 1. And Z sub 1 is at the the initial frequency and the initial capacitor. So that's 1 over J omega 1 C1. Again, comparing the denominators in this expression, the omega 1s are the same, the J's are the same, and we see that we have K sub F C sub 2 is equal to C sub 1, or the final capacitor is the initial capacitor's value divided by the frequency scaling K sub F. Now the nice thing about this is we can, in one step, combine frequency scaling and magnitude scaling, and sometimes that's necessary to accomplish the frequency scaling, and matching parameter values. So if we combine both magnitude scaling and frequency scaling, we now go back with the inductor. Frequency scaling, there's no K sub F. There is a K sub M. So to get the final value of our resistor when we magnitude and frequency scale, we simply scale the initial resistor value by the magnitude scaling K sub M. For our inductor, we had a K sub M upstairs and a K sub F downstairs, so we take that ratio and use that ratio to scale the initial inductor to find our final inductor value. And for capacitors, both the magnitude scaling and the frequency scaling are in the basement. They combine to divide into C sub 1, the initial capacitor, to find our final capacitor value. And that's now how we would do magnitude scaling and frequency scaling to modify our parameter values to achieve the bandwidths that we want with the parameter values that we maybe have.